Thank you, Cindy. Thanks to the Humanities Festival and the Science Council and the Oriental Institute and all of you folks for waking up on a Saturday morning to hear a lecture about quantum mechanics. This makes me feel good about the state of the world when not everything does. Why in the world would anyone write a book about quantum mechanics is the first question you should be asking yourself. The cover of my book that just came out. It's not that quantum mechanics is uninteresting, but there have been a lot of books written about it already. In fact, one of the things I did for research for my book was to go to Amazon.com and type in the word quantum to the search bar, looking for titles of books. And there's Quantum Physics for Babies, which is a good book, actually, that I recommend. But there's also quantum yoga and quantum leadership and quantum touch and quantum meaning and quantum spirituality and a whole bunch of other things which I'm sure do not involve any equations whatsoever. I think that quantum mechanics has suffused the public imagination as something that is clearly very important and also something that is mysterious and not really quite understood. That's why I think it's important to write yet another book where finally I get to set the record straight and explain how things really are. It's not just quantum woo that is the issue. Science writers and professional scientists tend to emphasize the mystery of quantum mechanics, and they give people the impression that it is impossible to understand it. You might think that, of course, well, maybe it's impossible for me to understand it, but the professionals understand it. So I will quote my predecessor at CalTech, Richard Feynman, who's a famous physicist, who says, "I think I can safely say that nobody understands quantum mechanics." Usually I don't like to appeal to authority, but I'm appealing here not to say that something is true, but to say that physicists don't think that they understand their own subject. And when I quote this, I wrote a New York Times article quoting this, and of course, there were a handful of physicists who emailed me to say, I understand quantum mechanics. But I think what Feynman's quote should be interpreted as is physicists don't agree on what quantum mechanics says. Now, I'll get into what quantum mechanics actually is in a second, but let me first just mention that it's incredibly central. Quantum mechanics is the most important aspect of all of modern physics. You can't understand lasers or transistors or how the sun shines or why this lectern is solid without quantum mechanics. Quantum mechanics is at the middle of all of modern physics. And so you might think that if we have a theory that we know is really important, we can use it. But we use it in the same way that you use your car or your smartphone. You know what buttons to push to get it going. You don't know what's going on inside. And that's what Feynman is referring to. We don't really understand what is going on at the center of this theory, which we all agree is the most important theory we have. Now, you might think, under those circumstances, that the quest to understand quantum mechanics would be the single most important goal in all of physics, right? There would be academic superstars who spent their time thinking about how to understand quantum mechanics, and the University of Chicago and Harvard and Stanford would throw huge salaries at them to attract them because it would be the most important thing we can do. That is not how it is. In fact, if you're a young person, a graduate student who expresses interest in trying to understand quantum mechanics at a deep level, you are fired. Or at least you're told to, shape up and do more important things. And so the way that I like to think about it is, there's a fable by Aesop, one of Aesop's fables about the fox and the grapes. Do you know this one? The fox sees the grapes, they're very juicy and they look yummy, and the fox says, I want these grapes, and the fox jumps up and down trying to get the grapes, but they're out of reach. The grapes are just too high up there. So the fox eventually says, you know what? I never wanted those grapes anyway. They were probably sour. Okay, you're not supposed to explain your parables, but just in case it's not clear, the fox represents physicists. The grapes represent understanding quantum mechanics. We tried to do it back in the 1920s and 30s. We failed, and now, since then, we've been telling ourselves we never wanted to do it in the first place, that understanding quantum mechanics is not important. I think that's completely wrong, and that's the real reason why I wrote the book, is to fight against that tendency to think that understanding how nature works isn't what physics is really about. So let me tell you how we got here a little bit. This is going to be a potted history that ignores a lot of details, but it gives you the basic idea. By 1909, we had this picture on the right. You know, this is a picture you've seen before, the cartoon of the atom, okay? This is properly called the Rutherford atom. Ernest Rutherford put this picture together. There was before this picture that we called the plum pudding model of the atom, where an atom, you know, which is the stuff that makes up you and me, all the chemical elements, was thought to be this blob with little dots, which were electrons inside. Rutherford, by shooting atomic nuclei at gold foil, what he noticed is that usually they would just zoom right through, but occasionally they would bounce right back. So rather than being a big puffy thing, an atom is actually a concentration of mass in the middle, which we call the nucleus, and then little light particles called electrons orbiting around it. And we now know, much later, that that nucleus is made of protons and neutrons, but this basic picture is what we teach each other. This basic picture has appeared everywhere. It's the standard representation of an atom. It looks like a little solar system, right? It looks like the nucleus is like the sun, the electrons are orbiting like planets. This picture is entirely wrong. And we knew it immediately. We knew it immediately in 1909. We knew this couldn't be the case because quantum mechanics had not yet come on the scene. People were still operating under the assumption of what we call classical mechanics, Newtonian mechanics. In the 1600s, Isaac Newton gave us this wonderful picture of how the world works. If you tell me the positions and the velocities of all the particles in the universe, I can tell you where they're going to go. This is classical Newtonian mechanics. It was so good that people didn't even contemplate that it might be wrong, classical mechanics. It was a paradigm. It was a way of doing physics. If you apply that paradigm to this little picture of the atom, what you see is these electrons, you can calculate how quickly they're orbiting, and the answer is really, really quickly. So if you take an electron, that's a technical thing, but you know, there's detail. If you take an electron has an electric field around it, and the electric field points toward the electron. So if you take the electron and you move it, the electric field adjusts. But it doesn't adjust instantly all over the universe because it takes time for the information to propagate out. So there's a ripple that goes out. And if you take that electron and jiggle it up and down, a wave is emitted, and we call that wave light, electromagnetic radiation. Literally all the light in this room is coming from electrons jiggling up and down. So these are electrons jiggling up and down. They should be emitting light. And what that means is those electrons should be losing energy. They shouldn't just sit there calmly orbiting in fixed ellipses or circles. They should lose energy and spiral into the middle of the nucleus. And you can figure out how quickly that should happen. The answer is 1/100th of a billionth of a second. So we can do that experiment. Ready? Okay, we did it. The electrons did not collapse into the centers of the nucleus. All of the stuff in this room, the stuff you're made of, all the planets, the sun, and everything should collapse to a point if this picture of the nucleus was right and classical mechanics was right. Something has to give. Of course, your first guess is that this picture is not quite right, but eventually, you know, they tried really hard, and there's this whole other part of the story where people like Max Planck and Albert Einstein said, light, even though we know it's a wave, has particle-like properties. So some brilliant physicists, especially Louis de Broglie, said maybe the particles, like the electrons here, have wave-like properties. Maybe there's this weird mixture between being a particle and being a wave. That turns out to be right. The solution to making the atom stable, understanding why the lectern does not collapse, is that electrons are not particles. You should think of electrons as waves, and there's a wave that spreads throughout all of space, but it's concentrated somewhere, and it's kind of like if you take a violin string and tie it down on both ends and pluck it, you know you can get different frequencies coming out, but there's a certain set of frequencies, right? You get the fundamental, and then all the different overtones and so forth. Likewise, for the electron near the nucleus of an atom, there's certain ways the electron can settle down to. A little blob that is spherically symmetric, and then circles around it, and then all these orbitals that plague your nightmares from chemistry class when you were in high school or college. This is where all those orbitals come from. The idea of the electron is really a wave. That's why electrons do not just decay. There's the lowest energy way for the wave to be, and that just sits there and makes the atom stable. Good. That's progress, and then even more progress came soon thereafter when Erwin Schrodinger attached an equation to this wave. This is called the wave function, capital Psi, the Greek letter psi, is what is the Very unelegant name we give to this wave that represents the electron. And Schrodinger's equation tells us how the wave function evolves. And I've written it out here because it's going to be part of your problem set that I give you at the end of the lecture. Solving Schrodinger's equation is one of the favorite things for physics students to do, let me tell you that. We actually don't need the details of this equation. What matters is there's an equation. Okay, so now it's not just some vague hypothesis like electrons are a little bit wavy. Now it's a full-blown replacement for Newtonian mechanics. Instead of Newton's laws of motion, right, F equals ma, force equals mass times acceleration, Schrodinger's equation replaces that. The electron is not a particle, it's a wave, and this is the equation that it obeys. So far, so good. You think that maybe we're on the right track, right? Okay. Here's why it doesn't work. Because when you look at electrons, they don't look like waves. They look like particles. This is a little sample of uranium put into a cloud chamber, which means that when the uranium emits a radioactive decay, when there's a charged particle that zooms away from the substance, it is detected by the cloud chamber around it. So these little lines that you're seeing coming from the little rock there are particles being emitted by the uranium, different kinds of particles. And what you notice is, I could have used Schrodinger's equation, I could have predicted, using quantum mechanics, as we call it, what the wave should look like when a particle is emitted from a decaying substance, and the answer is it comes out more or less uniformly. Waves tend to be big, puffy things that spread out in all directions. But when you look, you don't see big, puffy things spreading out in all directions. You see a line, a little trajectory, as if it is like a particle. So it's almost as if the electron is acting like a wave, but only when we're not looking at it. And when we look at it, it begins to act like a particle. This is obviously crazy talk. And physicists, applied their brains to figuring out what could be really going on. And they came up with the following theory. Electrons act like waves when you don't look at them, and they act like particles when you do look at them. Brilliant. This is called the Copenhagen interpretation of quantum mechanics. And it says that there's a truly different way that the fundamental constituents of the world act depending on whether we're looking at them or not. When we're not looking at them, they're waves that obey that equation, Schrodinger's equation. So here's a wave function all spread out over on the left. And then when you look, it suddenly localizes to look like a particle. And you want to say, well, where does it localize? We don't know exactly. We cannot predict with any certainty where we will see the particle. The best we can do is to predict the probability of seeing it in different places. And the probability depends on what the wave function was before you looked. Where the wave function is big, there's a high probability of seeing it there. Where the wave function is small, there's a low probability of seeing it there. So I'm not going to now tell you, but since then we've learned better. This is what we teach our students in the University of Chicago, for example, or CalTech, or any other university where we teach quantum mechanics. This is enshrined in the textbooks as how quantum mechanics works. There are two sets of rules. There's the rules on the left when nobody is looking at the quantum wave function for a particle or a system or anything. It's very straightforward when you're not looking. It's kind of like classical mechanics, but it's waves instead of particles. No big deal. There's a quantum state, the wave function, there's an equation for it, the Schrodinger equation. We're happy. This is the kind of thing that makes physicists pleased. But then when you look, all hell breaks loose, okay? You can't say what you're going to see exactly. The wave function suddenly changes, and all you can do is predict the probability, and the probability depends on the wave function squared, okay? This is what we teach. This is what was established in 1926 and 27. It's still what we teach our students today. So to drive home the weirdness of this, we will appeal to the thought experiment stylings of Erwin Schrodinger and the famous cat experiment, okay? So for those of you who are lucky enough to have never heard this before, the idea is that Schrodinger was in correspondence with Einstein. Schrodinger and Einstein and a few other people resisted this Copenhagen interpretation of quantum mechanics. They said, Surely you don't believe this, right? I mean, okay, it's a fine stopping place along the way, but the journey isn't over yet. We should keep trying. We should do more. We should figure out what's really going on. And Schrodinger's cat was not a thought experiment that was the goal of which was to say, ooh, isn't this weird? It was to say, surely you don't believe that this is what's going on. So Schrodinger says, imagine like our picture of uranium, there's some radioactive substance, and there's a Geiger counter or some other detector. So there's a quantum wave function for the source that is what we call a superposition. Just like the electron could be in a superposition of every different possible location, and we're going to see it in one location when we look. The source is in a superposition of I've decayed and I have not yet decayed. And that's a microscopic quantum mechanical thing, fine. What Schrodinger wants to do is to amplify that quantum behavior to the macroscopic world to make it seem ludicrous. So he said there's a detector. If this is all in a closed box, by the way, because the point is no one's looking at it. So Schrodinger wants to exemplify what happens when you just obey the Schrodinger equation, when you don't observe the system. So the source is in a superposition of I've decayed and I've not decayed. Therefore, the detector is in a superposition of I've detected a particle and I've not detected a particle. And when the detector detects a particle, it lifts the box off of the lid off of a littler box that contains some gas. Now, there's a cat in the bigger box, and in Schrodinger's original experiment, inside the box, the littler box, there was cyanide, and it killed the cat, okay? And in the words of Schrodinger's daughter, I think my father just didn't like cats. So we don't need to do that. For the purposes of the thought experiment, I am replacing the cyanide with sleeping gas, okay? So what happens in Schrodinger's cat's thought experiment is that the cat evolves, according to the rules of quantum mechanics, into a superposition of being awake and being asleep. There's the cat happily asleep or awake. And the point is, the rules of quantum mechanics say, it's not that it is awake or asleep, we just don't know. It is literally in a superposition of both. And Schrodinger wants you to say, surely you don't believe this. So just to draw that distinction, a classical cat there could be a cat in the box, and everything classical I'm going to put in square brackets, and everything quantum henceforth will be in parentheses. So you might not know whether a cat is awake or asleep. For those of you who are not cat owners, it's probably asleep. But still, sometimes the cat could be awake, and you just don't know. That's okay, but the quantum thing is a little bit different. Quantum mechanics is a truly different kind of thing than classical mechanics ever was. And so it says the quantum cat can be in a superposition of being awake or being asleep. And then the point is that that situation holds until you observe what's going on, and that's when you open the box. So in the Copenhagen interpretation of quantum mechanics, what happens is that there is a quantum mechanical system inside the box, but the observer is classical. So in this little diagram, the role of the observer is played by Niels Bohr, who is one of the leaders of the Copenhagen interpretation of quantum mechanics. So the observer is classical. The cat, the quantum system, is in parentheses in a superposition. The observer opens the box. The wave function of the cat collapses, just like the wave function of an electron would collapse. And either the cat's awake and the observer saw it awake, or the cat's asleep and the observer saw it asleep, okay? And so there was a superposition up until the moment of observation where it suddenly changes. And the point is, you can't possibly believe this. And this is what people like Einstein and Schrodinger were arguing, like not small fries, okay, in the physics world, kind of big names. And yet, the entire physics community ignored them and said, yeah, that's more or less what I believe. That's what we're going to go with. That's what we're going to have for the next 90 years of physics, okay? So that's clearly unacceptable as a fundamental theory of nature, and in their more honest moments, physicists sometimes admit this. Let me just mention two of the problems that we've glossed over if you really wanted to take the Copenhagen interpretation seriously. First, and I think most obvious, is what I call the reality problem. I talked about a wave function, a superposition. The electron is this wave, or the cat's in a superposition of awake and asleep. So what is that? What do you mean? Wave function. Is that supposed to be a direct representation of reality? That's like an isomorphic map between the mathematical formalism and the real world? Or is it just a partial representation of reality? I mean, maybe there's a wave function, but there's also other things. Or maybe it has nothing to do with reality. Maybe the wave function is just a tool we use to characterize our ignorance about what's going to happen, and there's some way of talking about reality which is entirely different. We don't know. All of these options are very much on the table here 90 years later, 90 years after we started down this road. And we haven't even been thinking about which one of these is right, which is why many discussions of quantum mechanics, even by professional physicists, are very confused and confusing. They don't know what reality is. They don't know if the wave function is real or not. You ask a physicist, is an atom mostly empty space? Often they will say, yes, and a little electron is a point, it's very small compared to the atom. That's complete nonsense if you think that electrons are wave functions. The wave function fills up the whole atom. There's no empty space there at all. These very basic, easy-to-ask questions have no answers that physicists consistently give. The more famous question is called the measurement problem, and this is even more obvious when we look at that formalism that I gave you. What do you mean measure, look at? I mean, come on. That you can't possibly have something that is that vague and ill-defined play a crucial role in your fundamental theory of reality. You need to tell me what you mean. Does it need to be a person? Can the cat observe itself? What if there's an earthworm in there? What if it's a person who just like is short-sighted? What if they only glance at the cat, right? Like, what if they listen to it? Does that count? What if there's a video camera? What do you mean? How quickly does it happen? When does it happen? It's supposed to be a rigorous scientific theory. You have to be able to answer these questions. And the Copenhagen interpretation just says, don't worry about it. And this leads people to wonder whether or not the idea of consciousness, and there's something special about the human mind that influences or maybe even brings into existence the external world. And this opens many cans of worms, and you end up with Amazon.com titles on quantum yoga and quantum leadership and so forth. Okay. It's not that nobody worried about these problems. There were people worried about these problems. It's just that they got kicked out, okay? So there are right now a number of perfectly respectable answers to these questions, and the problem is not that we can't answer them, the problem is we don't know which answers are correct. My favorite answer was invented by this guy, Hugh Everett, who was a graduate student who then got kicked out of the field. So in 1950s, Hugh Everett did a little bit of what I call quantum therapy. You know, his answer to all these questions about what is real and what happens when you make a measurement and so forth was basically to say, chill out. Relax, you're working too hard. Believe your theory. You have a theory, there are wave functions, they obey Schrodinger's equation. Cut it out with all the nonsense about observations. Just take your theory at face value and ask what happens. That was his prescription. So here is Everett's version of quantum mechanics. There's only one set of rules. There's not two sets of rules. There are rules that are obeyed all the time. Systems are described by wave functions, and the wave functions obey the Schrodinger equation. There's no separate rules for wave functions collapsing, or probabilities, or unpredictability, or any of that nonsense. This is what we call the Everett interpretation of quantum mechanics. Now, why isn't this obviously true? Well, we already told you the problem, that when we actually do experiments and do measurements, it looks like wave functions are collapsing. So, I mean, it's easy for Mr. Everett, later Dr. Everett, to say wave functions don't collapse, they just obey the Schrodinger equation. But then how do you explain the measurements? How do you explain that picture of the particles coming out of the uranium? And Everett says there's two things that you're neglecting, two things that you forgot that you should really take into consideration. Number one, you're not really classical. Sorry, you're a big observer, but you don't obey the rules of classical mechanics. You're made of atoms. Atoms are made of particles. Particles obey the rules of quantum mechanics. You are just as quantum as anything else. There's a wave function for you, just as there's a wave function for electrons. That's number one. The other is there's a feature of quantum mechanics that was really emphasized by Einstein in a famous paper in 1935, the Einstein-Podolsky-Rosen paper, where there's something called entanglement. I just said that you have a wave function just like electrons do. That's not really true. It's actually only one wave function for the entire universe, what Everett called the universal wave function, and which we've later called the wave function of the universe. We're not very good at naming things in quantum. Maybe that's why progress is so slow in quantum foundations. And because there's only one wave function for everything, things can be entangled with each other. And this phenomenon of entanglement is really at the heart of quantum weirdness, the heart of why quantum mechanics is so different than classical mechanics. And so all Everett's doing is saying, treat yourself as quantum, take entanglement seriously, ask what happens. So let's try to do that. So what do I mean by entanglement? Entanglement is the idea that what you would observe about two different parts of the universe can depend on each other. So I like to think about the Higgs boson. The Higgs boson was discovered just in 2012. You know, we have a lot of elementary particles, right? Quarks and electrons and neutrinos and so forth. And interestingly, almost all these particles spin, which means that there's a certain intrinsic amount of rotation or angular momentum that every elementary particle has. There's no electron sitting there that is not spinning, okay? No quark that is sitting there not spinning. The Higgs boson, which was only discovered in 2012, is the only elementary particle we know of that has zero spin. And that makes it very interesting because a Higgs boson can decay into, let's say, an electron and a positron, an anti-electron, okay? So if a particle with zero spin decays into two spinning particles, spin is conserved. Angular momentum, just like regular momentum, is conserved. So zero angular momentum has to go into zero angular momentum made out of two spinning particles. So we know that those two spinning particles have to be spinning in the opposite direction. We'll call it spin up if it's spinning clockwise when you look along its axis, and spin down if it's spinning counterclockwise. So you know that the Higgs boson is going to decay into a positron and an electron that are spinning in opposite directions, but you don't know which direction either one of them is spinning in, okay? I'm being a little bit sloppy with the language here because really it's a superposition of both. So you have two particles moving in opposite directions, particle 1, particle 2. They're both spinning. Particle 1 could be spin up, or it could be spin down. Particle 2 could be spin up, or it could be spin down. But we know that whatever one is doing, the other's doing the opposite. Okay, this is an empirically measurable fact about particles. That's what it means to be entangled, because we can take particle 1, particle 2. If you say, I'm going to measure the spin in particle 1, I have no idea what answer I will get. It could be spin up or spin down, 50-50. If you take particle 2 and say, I'm going to measure that spin, you have no idea. It could be spin up or spin down. But if I measure the spin of particle 1 and I get spin up, then I instantly know that particle 2 is spin down, and vice versa. That's what entanglement means. There's a relationship between the possible observational outcomes for two different parts of the universe. And what concerned Einstein about this was you could make these two particles and you could send one of them to Alpha Centauri, 4 light years away, without looking at them, and then measure your particle here. Oh, it's spin up. You instantly know what the particle on Alpha Centauri is. How does it know? It's 4 light years away. He called this spooky action at a distance. And this is an issue with quantum mechanics, but it's also been experimentally verified. It's true. That's how quantum mechanics works. So just to drive this home, this is what entanglement is. I'm going to say exactly the same thing again in slightly different words. There are not separate wave functions for each particle. In other words, in classical mechanics, when you have a big system that's made up of a lot of little things, in principle, I can specify all the little things separately. Okay? They have their own states, their own things that they're doing. In quantum mechanics, you can't do that. You might think, if I have a positron and electron, there's a wave function for the positron and a wave function for the electron. But that's not how quantum mechanics works. There's only one wave function for the entire universe. So for these two particles, for example, that can be entangled. There can be a relationship between them, okay? Why do you care about this? Why do you care about entanglement? Well, watch. Here's the Schrodinger's cat experiment, done again, but now from an Everettian point of view. Remember, the two additions are your quantum as the observer, and you can be entangled. So you treat both the cat and the observer as quantum. Now the observer looks like Hugh Everett. And you don't have any weird rules for measurement or anything like that. Systems always obey the Schrodinger equation. And by systems, I include you. So you open the box, you look at what's inside, and the answer to what happens is just whatever the Schrodinger equation says happens. So you open the box, you call that measurement, but it's not different than anything else. It's just what the laws of physics say will happen. And what do they say? They say with 100% clarity that you and the cat evolve into a superposition of the cat was awake and you saw the cat awake, plus the cat was asleep and you saw the cat asleep. So you have a wave function. You have become entangled with the cat. You are in a superposition, okay? It's not that you saw the cat awake or the cat asleep. You saw both. And again, everyone agrees that this is what the Schrodinger equation predicts. The Copenhagen interpretation goes on to say, but that would be wrong, and so it erases randomly part of that wave function. But what the Schrodinger equation says is not ambiguous. It says this. And the puzzle is, no one has ever looked at a quantum system and felt like they saw both answers at once, right? That's the problem. The problem is that we've never experienced, apparently, what it's like to be in that particular state. So non-Everettians say like, that can't be right. Now, I did actually leave something out. I don't know if you caught my little sleight of hand here. I've been emphasizing that there is only one wave function for the entire world. And yet, I wrote down a wave function for a cat and a person, which is a pretty meager world, right? I mean, there's a whole world out there. Honestly, I should include the rest of the world, shouldn't I? So there's something called decoherence, which is going to help us answer this question here. So because I want to include the rest of the world, I'm just going to lump the entire rest of the world into something I call the environment. Those little leaves of grass there, okay? You can think of the environment as literally everything else, but in particular, like the individual photons of light in this room, or the air molecules, all these things that are going on that we're not keeping track of. We don't know where every photon is or whatever. But how the photons or how the air molecules behave depends on what the cat's doing, right? If the cat's asleep, a photon might miss it, but if the cat was standing up and awake, the photon might hit it. So long before you open the box, the cat becomes entangled with the environment. And the environment is not like trees in the forest. The environment is everything going on in the box other than the cat, okay? So yes, the cat interacts with everything else in the box. Remember, we worried, does it count if it's a virus or an earthworm doing the observation? Here's where this gets answered. The rest of the universe is constantly monitoring the cat, not actively and intelligently, but bumping into it. So the environment, everything else in the universe, becomes entangled with the state of the cat long before you open the box. This is a phenomenon called decoherence, and so you get cat is awake, environment has seen that the cat's awake, plus cat's asleep, the environment's seen the cat's asleep, and you have not yet opened the box. Then you open the box and you become entangled with everything, okay? So at the end of the day, again, everyone agrees, this is the prediction of the Schrodinger equation, there's this complicated wave function with two different parts. Cat's awake, the environment saw it awake, you saw it awake, plus cat's asleep, environment saw it asleep, you saw it asleep. How should we think about this? Again, we still have the problem. It never felt to me like I was in a superposition, right? But I appear to be. But really, I'm not in a superposition. I'm entangled with the rest of the universe, right? So here's Everett's genius move. He says, look, whatever happens in that first part of the wave function, the part where the cat was awake and the environment saw it awake, etc., if I changed something, if I went in there and by hand affected that part of the wave function, it would have zero impact, zero influence on anything that happened in the other part of the wave function. It's not like, here in this room, if I knock over the bottle, it affects the floor because water falls on it and so forth. What happens in that one part of the wave function has no influence whatsoever on what happens in the other part. The two parts of the superposition behave and evolve entirely separately. It is as if they have become separate worlds from each other. So Everett called his theory the relative state formulation of quantum mechanics. Again, not exactly box office. It was later dubbed by Bryce DeWitt the many worlds interpretation of quantum mechanics, and that has caught on, and that is what we call it now. But the point is, we didn't put in a bunch of worlds, okay? We didn't take quantum mechanics and say, maybe it just doesn't have enough worlds in it. All we did was take seriously the Schrodinger equation. If you believe that an electron can be in a superposition of two different spins, if you believe that a cat can be in a superposition of awake and asleep, you should believe that you can be in a superposition of having seen the cat awake and having seen the cat asleep. You should believe that the universe could be in a superposition. And the only question is, do those superpositions get created by the natural evolution of the universe? And the answer is yes, they do. And once they do, they act independently. It's as if they're completely separate worlds, okay? So this is Everett's big idea. This is the thing we're going to try to wrap our heads around. It seems very natural and very inevitable that through the ordinary evolution of quantum systems, you and I get duplicated all the time. In a typical human body, there are roughly 5,000 radioactive decays per second. So you have split not just into 5,000 copies, you have split into 2 copies 5,000 times every second. So that's 2 to the power 5,000 copies of you that are being created every second. And that's just you. You're not even trying hard, right? I mean, there's plenty of other things that are branching, as we say, the wave function of the universe. So the implications of this are a little mind-boggling, but the implications are just what the Schrodinger equation predicts. The question is, are you willing to accept that that's how reality actually works? There are objections. Some are really good objections. I'm going to hide those from you, but I'm going to tell you the bad objections, okay, so we can get on to make progress on something else. Here are some easily answered objections. One is that the real objection is that people just don't like it. They get a little weirded out by the idea that there are multiple copies of themselves being created all the time. Well, you know, we didn't, again, change quantum mechanics to make that happen. That happened automatically. The question is not, you know, did you make quantum mechanics more complicated? The only question is, do you accept it? And the math is clear that it makes sense if you want to go that way. If you want to invent a different version of quantum mechanics, you can do that. Every other version of quantum mechanics is a disappearing worlds version of quantum mechanics, and that's perfectly fine, but tell me exactly what you mean by that, and then we can go test it experimentally. Which is, by the way, the other objection. People say, well, I don't know how to test this theory, it's just theology, it's not really physics, all these other worlds, I don't know where they are. The problem is, not the problem, but the reality is, we didn't put the worlds in. The axioms of Everettian quantum mechanics are not, there's a bunch of worlds. That's a prediction of the theory. That's not the essence of the theory. The essence of the theory is there are wave functions and they obey the Schrodinger equation. These are highly testable axioms. We can easily test the Schrodinger equation. We do test it. We are testing it. There are experiments going on right now looking for tiny violations of the Schrodinger equation. And if we observe those, we will know that Everettian quantum mechanics is false. It is the most falsifiable theory ever. Just because it makes some predictions that can't be tested doesn't mean the theory itself is not testable. Finally, there's the worry that it seems to cost a lot of energy to make whole new copies of the universe, right? Like we live in a universe, there's stuff, there's tables and so forth. You're saying I'm making multiple copies, doesn't this cost energy? What about energy conservation? Don't worry about that. And honestly, I say that because this is one of those questions which the math is entirely straightforward for this one. I mean, there's just no question that this is a worry if you go through the math, but it's really hard to translate the math into English. The best I can do is to say, when you should think about this wave function branching, the wave function, it's better to think of it as splitting rather than being duplicated. There's a certain amount of universe, a certain thickness or weight to the wave function, which just gets subdivided over time, but the total weight remains the same. So every universe, even though the people in it perceive it as just as much of a universe as before, the universe is getting thinner over time. So we can be thankful for that, I think, rather than being upset, that we're really getting thinner in some cosmic sense. Nevertheless, despite the fact that this is an awesome theory, there are alternatives, and you can read about them in my book. I mentioned them. So let me just mention 2 of them just to drive home how sort of desperate people get to avoid the implications of Everettian quantum mechanics. One are hidden variable theories. So if you're worried about the idea that electrons behave like particles sometimes and waves other times, it's logical to imagine that maybe they're both. Not both at the same time, but there are waves and there are particles involved in the fundamental constituents of reality. So what is called Bohmian mechanics says there is a wave function, but the wave function is not what you observe when you look at the system. The wave function is what's going on when you don't look, but when you observe, you see these other little degrees of freedom, these other little variables, which are actually particles. That's why you see particles. It's a very natural kind of idea. Why do you see particles when you do experiments? Because there really are particles in addition to the wave function. There's problems with this kind of theory, especially making it compatible with modern physics, but it's very viable as a possible alternative to Everett. The other popular alternative are spontaneous collapse theories. These theories say that the wave function really does collapse, but not when you look at it. There's nothing weird about consciousness or perception. They just collapse all by themselves. It's very, very rare. One particle has its wave function collapse once every few 100 million years. But in a big macroscopic system, there are many, 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 many particles. And so they sort of maintain some classical location in space for exactly this reason. So the alternatives are there. They're experimentally testable. I think that they are hurting us in a very straightforward way. So I want to shift gears here near the end of the talk. One of the big questions about Everettian quantum mechanics is, why should I care? Of course, the real reason is because we want to understand the fundamental nature of reality. But you might want to be a little more practical than that. Does this change of perspective help us answer any other questions, or is it just out there all by itself? So my personal belief is that we have been hindered in the rest of fundamental physics by the fact that we have not stood up to the challenge of understanding quantum mechanics. Even professional physicists who work with quantum mechanics all the time still don't quite internalize it. When we learn quantum mechanics as physics students, when we grow up to become professional physicists, when we construct a theory of something, the theory of the electromagnetic field or the theory of gravity or whatever, we tend to start with a classical theory, and then we do what's called quantizing it, right? We turn that classical theory into a quantum theory. This is literally what everyone is taught how to do. But presumably, nature doesn't do that. Reality doesn't start classical and then quantize itself. Reality just is quantum mechanical from the start. So the way the logic should be working is that you should start with a quantum mechanical theory and show that there's some classical behavior in the right limit, in the right approximation, and so forth. But reality really is quantum from the very start. And my feeling is that part of the reason why we're stuck on certain problems in fundamental physics is because maybe these particular systems don't get quantized by starting with some classical theory at all. The classical theory is just this baggage that we're carrying around with us, and if we thought quantum from the start, we would make more progress. So let me very briefly, I'm close enough to the end of the talk that everything that I said so far is true. Everything I say from now on will be wild speculation that will be hard to understand, because that's in the nature of speculation. We don't understand it. We don't understand what we're doing. This is the cutting edge, the bleeding edge of theoretical physics. Here is the biggest problem we have right now in fundamental physics. It's quantum gravity. Here's this guy, Einstein. I like to show pictures of Einstein when he was young and well-dressed and combed his hair. When he was inventing these wonderful theories that changed the world. He let himself go a little bit later, okay? Maybe that was because of quantum mechanics, I'm not sure. But his biggest achievement, Einstein, was gravity, was understanding the nature of space-time. And first, Einstein said that we should think of space and time individually as different aspects of four-dimensional space-time. And then he said that space-time is not just a rigid background on which we move, it's flexible. Space-time is dynamical. It can be curved and warped. And those curvings and warpings are what you and I perceive as gravity. Literally, when an object falls, it's because the earth beneath our feet is warping the geometry of space around us. So there's a give and take. The geometry of space affects the evolution of matter and matter and energy affect the curvature of space. That is the motto of general relativity, Einstein's theory of gravity. Geometry of space-time is related to the energy, the stuff, the matter, the heat, the momentum. All the different forms of stuff cause space-time to warp and are affected by the warpings of space-time, okay? Sadly, Einstein's theory is completely classical. Even though it's relativity, it still obeys the paradigm of Newtonian physics. So obviously, you would like to turn it into a quantum mechanical theory. This was literally the thesis project that John Wheeler gave to Hugh Everett. He said, think about quantum gravity. And Everett got sidetracked by saying, but quantum mechanics doesn't even make sense. Let me think about that instead. So maybe that's not a surprise. You know, we've been trying to quantize gravity for these many years, and we failed. But we admit that we don't even understand quantum mechanics. Maybe it's not surprising that we can't understand quantum gravity if we don't understand quantum mechanics, right? Quantum gravity is just a particular theory within the quantum paradigm. So maybe I'm going to suggest that the strategy should be not to quantize gravity, but to find gravity within quantum mechanics, to start quantum, not from a classical theory like general relativity, and ask, you know, can we find a limit of this quantum theory where it looks like curved dynamical space-time, gravity, the whole bit? You know, we're allowed to take clues from what we know about the world, and what we know about the world is summarized in what's called quantum field theory. This is the idea the fundamental building blocks of nature are not really particles at all, they're fields, okay? Of course, when you look at an electron, it looks like a particle. When you look at light closely enough, you see photons. But that's just the magic of quantum mechanics. What's literally lurking underneath is that everything is a field pervading all of space. So you're familiar with this when it comes to the electric field, the magnetic field, the gravitational field. But even, according to the quantum field theory perspective, even things like electrons and quarks and neutrinos that you think of as particles are really vibrations in fields filling all of space, okay? So the difference is, if the world were made of particles, there would be particles, and in between the particles, there would be empty space. And empty space would truly be empty. That's the particle way of thinking. In field theory, there's no such thing as empty space. There's space in its lowest energy state, which we call the vacuum, but even in the lowest energy state, there are still fields there. Even if their values are zero or they're not doing anything, there's all sorts of quantum fields living at every single point in space. And what you think of as a particle is not something new at that location, it's just the field is vibrating more at that location, okay? So this picture of quantum field theory says that even empty space is buzzing with activity. It's a much more fun place to be than in a particle theory. And you'll be unsurprised to learn that even in empty space, these different regions of space are entangled with each other. So here is just a picture of empty space in quantum field theory, right? No particles or anything like that. I can take a region here, a region here. I know that there are vibrating quantum fields, and I can ask, are they entangled with each other? And the answer is yes. And the answer is that the closer they are in space, the more entangled they are. When they're further away, they're not as entangled. That kind of makes sense. They're interacting more strongly if they're nearby, not that much when they're far away. So that is what we're taught in quantum field theory classes and so forth. What I want to suggest is that maybe we can turn that around. What we're taught in quantum field theory is the closer you are, the more entangled you are, if you're a vibrating quantum field in empty space. What I want to say is closer is a derived concept. It is a higher level emergent phenomenon. There's no fundamental notion of space or distance or anything like that. All there is quantum mechanics. So rather than saying I have the distance between 2 points and I derive how entangled they are, I want to say I have how much two different quantum things are entangled, and I want to use that to derive how far away they are. So I will define what it means to be a certain distance between 2 points by how entangled they are. The more entangled they are, the nearer they are. So what I can do is derive an emergent notion of space itself based on entanglement. So Einstein said there's a relationship between geometry and energy. Here, quantum mechanics is saying there's a relationship between geometry and entanglement. Meanwhile, there's also a relationship between entanglement and energy. Remember I said a particle was when I take a little quantum field and I vibrate it more. When I do that, I break the entanglement between what would have been a vacuum mode, an empty space, zero energy, lowest energy state vibration. I make it more energetic, and I make it less entangled with the world around it. So whenever I have stuff in a region of space, a star, a planet, a whatever, that region is less entangled with the region around it. There's a relationship between entanglement and energy. So you see what naturally falls out of this perspective. We start with entanglement. We don't start with space and time and fields. We start with pure quantum mechanics and this idea of entanglement. And we show that we can derive the geometry of space with some simple assumptions, and we can also derive the energy within space. And you can even show mathematically that the relationship between geometry and energy is exactly what Einstein said it was. In other words, at least, again, under many assumptions that are a little dubious and certain limits, certain approximations, when you derive the existence of space from pure quantum mechanics, it is very natural for the geometry of that space to obey Einstein's equation of general relativity. So maybe, we don't know yet, we're working on it, but maybe rather than trying to quantize some classical theory of gravity like general relativity or superstring theory or whatever, we can find emergent gravity lurking there within quantum mechanics all along. Stay tuned for that. We're still at work on that, but it's a very exciting prospect. So I will leave you with a thought from David Deutsch, who was one of the primary proponents of the many worlds interpretation of quantum mechanics. And he says, despite the unrivaled empirical success of quantum theory, the very suggestion that it may be literally true as a description of nature is still greeted with cynicism, incomprehension, and even anger. So I'm hoping that at the end of today's talk, at least the incomprehension will be a little bit less than it was at the beginning. Thank you very much.